What is good, YouTube? You know what we talking about today? We talking about logarithms, okay? We talking about not the exam, not the tests that we go out and we study hard for every single day. We talking about logarithms, okay? And if you don't know this reference, you don't know Allen Iverson, you can ask your dad, look him up on YouTube, I don't know. But for now, before you do that, don't get distracted. Let's learn some logarithms together. Let's go. Alrighty, hey guys, welcome to Mullet Math. I am stoked to get started here on logarithms, but we're gonna jump through this first part pretty quickly because I'm just kind of giving you a basic idea of what you would use logarithms for in the real world, right? You're gonna use logarithms in the real world when you have growth or decay. I wrote these down here just because typically that's when you're going to see exponential functions, right? A growth or decay function. But two good examples, if you have a monthly mortgage payment, right? And this is your little function here for your monthly mortgage payments. And let's say you wanted to isolate n, right? The total number of payments that you're going to make. You can do so using logarithms. I'm not going to get into it because it's a lot of algebra and we don't have time for that in this video. But also looking at like a compound interest rate, you would put money in a compounding interest account, and let's say you want to look 30 years down the road and you want to know how much interest you'd get, or you wanted to manipulate this t variable up here, right? You can manipulate that t by using a logarithmic function, getting the t out of there, and then solving for that, right? So just two basic examples of kind of why logs are useful in the real world and what we'd use them for. So with that, we will segment our way into 1 and 2, our theory and conceptual parts of logarithms. So I want you to take some time here, maybe pause the video if you haven't seen these equations before, because they are very, very fundamental and important to what we're going to be talking about later in this video. So pause the video, write these down if you haven't done so already. But hopefully you've seen this in a class before, whether your teacher or professor has shown you these and you've talked about it a little bit. But let's go into equation number 1. So you have the log base a of x and y, two variables, right? You can split that up into log base a of x and log base a of y. Okay, that's equivalent. So the other thing to think about, if you're given a question where you have log base a of x plus log base a of y, you can just as easily write that and combine them to simplify it here as log base a xy, right? Pretty simple, straightforward, so I'll keep moving on here. Another simple, straightforward one is equation number 2, log base a of x divided by y, right? Those are two variables. That equals log base a of x minus log base a of y, okay? That's just a known factual equation that we have found in our past mathematical years as scientists, right? I'm going to consider you guys scientists here on this channel, but we're going to keep diving in here. So equation number 3, you have log base a of x raised to the r power. What we can do to manipulate that, we can bring r out of the equation and we can multiply it by the log base a of x, right? So we just take that r, we pop it out of the equation here, but we just turn it into multiplying it by this logarithmic function here. So r times log base a times x, right? Pretty simple there. Moving on, we have equation number 4. Now I did this separation on purpose here just to separate the basic log functions, right? If we have a basic log function, we assume the base is 10. Hopefully you guys have learned that, right? We'll assume that the base is 10. But when we get down here, we have something a little bit different. We have log base e. And what is e? Well, e is Euler's number, or Euler's number, depending on who you talk to. But I'm not going to go super in-depth about what E is in this video. You can go look up, I know Khan Academy kind of gets into it a little bit, and even I think the channel is called 3 Brown 1 Blue. Super good channel. They kind of go in depth of what's going on here, but just know that E is Euler's number. But we're going to kind of keep going. So you have log base E of x is actually equal to the natural log of x. And like I said, just be aware that these log terms, right, log base e, and we get into these natural logs, they are very different from a typical log situation where you have a base 10. So just making that distinction so you're clear. Moving on to equation 5, you have the natural log of x equals y. Well, we can also rewrite that pretty easily as e, there's our number again, right? E raised to the y power equals x, okay? So that's the theory. I won't get too far into it because hopefully your teacher and professors are teaching you that. So we're really here for steps 2 through 4, right? The conceptual, and then maybe doing some problems together. So I'm going to pop a little graph up here, hopefully to the left or the right of the video, just so you can see a graph of a logarithmic function and how it compares to the inverse of its similar exponential function, right? Because that's really what a log is. It is the inverse. It's the inverse relationship with an exponential function, right? That's what we're getting at. So typically log functions are written log with a base a. We've talked about that, right? We have this x value here, like you come up here. Our x value is our argument, we call it. And you all have that equal to a y value, which is actually the exponent, right? And the way that we should be looking at these logarithmic functions and actually saying it in our brain is when we look at this, we should be saying y, right? This exponent is the power I need to raise a, the base, okay? Y is the power I need to raise a to get our argument or our x value, okay? So say that in your head, y is the power I need to raise a to get x, our argument, okay? That is the way that you should be thinking about logs when you see it in this, or written in this functionality, right? When you see it in this form. Okay, so with that in mind, I kind of have a cheat sheet here that you can test out on your calculator. I urge you guys to go through and kind of test these out on your calculator and get some practice. But if you guys want to isolate one of the variables, right, that's what we're doing. We want to find a, so we want to find the base. And let's say we're given x and the y value, right? We have it written in this form, nice and easy to understand. We don't have a, but we have x and y. Well, we can find a by just taking that e, right, and raising it to the natural log of x divided by y. Now, I'm not going to get into why these equations work in this video. Just know that they are kind of cheat sheets and easy ways to use them in the real world, right? But be super careful when you're using this cheat sheet. I am putting that disclaimer out, right? You guys need to know the domain of the log function. For example, putting a y value of 0 here, it's not doable, right? That would be, you can't do it. Math says no, right? So be careful when you're putting a y in, because you might have an answer of y equals 0. So just be aware of that, right? And even when we get down here where we have a natural log of a, be careful what we're using for a here, right? Because I believe it can't be 0, or excuse me, it can't be less than 0, or it can't be equal to 1. So just be careful when we're using these, that you don't run into that issue or a teacher or professor is testing on that, okay? So moving on, but let's say we were given the two variables, the base and the exponent here. Let's say we're given a and y, right? But we want to find x, we want to find our argument. Well, we can set x equal to a to the y, right? That's what we were saying here. Y is really just the power I need to raise a to get x. Okay, so that one's a given, that one's easy. So hopefully that's pretty straightforward. And then we also move on to, let's say y. Let's say a and x are given, right? The base and the argument are given. To find y, we just set y equal to the natural log of x divided by the natural log of a, okay? So this is a super useful cheat sheet. Like I said, be super careful when you do these though, what you're putting in your denominator, and make sure it's actually gives you a real answer and a real number, right? Alrighty guys, so we got the calculator here. We're gonna dive on into this. So we want to solve, and in this example 1, we're gonna solve to find x, okay? So that's our variable here, x. Well, what I like to do when I approach logarithmic functions and when we're doing problems like this, I just like to kind of rewrite the letters, kind of like we saw on our last sheet, right? I want to rewrite it to where we have a base, an argument, and an exponent. Really? Right? That's really what it comes down to. So we're going to rewrite this. So we know 2. This is our base, right? Because we have a base. It's to a certain power, right? Which this time we have a variable x minus 5. So this is our, I'm just going to go like this so it's super clear. That's our y, right? And then you have your argument over here, your x, right? Because we have a base to the y, a to the y equals our x, right? That's what we were saying to ourselves in our brain. So let's just rewrite this really quick. So we can rewrite this as log, okay, base a2, our argument 3 equals x minus 5. That's our y, right? So now we rewrote this to 2, right, raised to the x minus 5, that's what we have up here, equals 3, okay? Well, we want to isolate this x because that's what we're solving for. That's what this question is asking for, right? So we really can just rewrite this using the rule that we had from our conceptual, right? We want to isolate y So if we come back here, we're going to isolate y, and we're going to say y equals the natural log of x over the natural log of a. Okay, so that's what we're going to do here. So we're going to say x minus 5, which is our y, right? I'm going to make that super clear. That's our y, equals the natural log of x, right? And our x value is 3, over the natural log of a, which is 2. Okay, so all we really have to do, there's really only one step, right? We want to get this 5 over here to isolate our variable x, and we have our answer, right? So we can just rewrite this. I'm going to come over here for space's sake and say x equals the natural log of 3 over the natural log of 2 plus 5, right? All we did was we moved that 5, we added 5 to this side, and we added 5 to this side of the equation. So now we have x equals the natural log of 3 over the natural log of 2 plus 5. And that is our final answer. We can box that in, okay? If you guys want to do this on your calculator and just get a number, you punch in natural log of 3 divided by the natural log of 2, and we just add 5 there, and that gives us an answer of 6.585. Okay, that's our number if we want to give it to our professor or teacher. Okay, so moving on to example 2 here. Little bit different here, but remember, if we go back to our theory page, I do notice something here where we have a subtraction, right? We have a log function, log of 50 minus log of 5, okay? And we have something here that says, well, if we have a log and it has the same base, we can rewrite this subtraction as x divided by y, okay? So let's do that. Let's rewrite this, okay? And remember, when the log is written with no base, right? This is log 50. This is our argument. We assume that it's 10, okay? So we're going to rewrite this as log base 10. And now our argument, because of that equation, we're going to take 50, okay, divided by 5, okay? It's going to equal our y, okay? And now we're solving for y here. And I can write this up here now that we have wrote it like this. Solve to find y, okay? All right, so if we figure this out, 50 divided by 5, we can do that pretty easily. Let's simplify it. We're going to write this as log 10. 10 equals y, right? We can do that legally. And if we go log, right, this is assuming base 10 on our TI-84 if you're using that, or TI-83. It assumes a base 10, so we have log of 10, base 10. That gives us our answer. This is all going to be equal to 1. So this was a fairly easy one. But, you know, if we want to check our math, we can use calculators and just do this straight off the bat. But I know some professors and some teachers like to show your steps and that you actually know what you're talking about here. But let's check this. Okay, let's go back to the original equation. Log of 50 minus the log of 5. Okay, theoretically, we should get the same answer. So boom, bada bing, bada boom. We are good to go. We have the same answer. I feel confident that we can move on. All right, hopefully that all made sense. And this is going to be just kind of the last segment of the video here. We got a real world problem, okay, real world problem. So we're going to have a fake scenario, but we have bacteria and it's going to triple, okay, so bacteria triples every minute on a petri dish, okay. The question is asking us, find how many hours it will take for the bacteria to reach a population of 2 times 10 to the 18. So that's a pretty dang big number. But we can do this pretty simply. We just got to write an equation out for it, right? And so if we're going to try to find bacteria, okay? So bacteria are capital B, and I'll define that over here. I'll say B is our bacteria population, okay? And we're going to set that if it's tripling, okay, in an exponential function like this, we'll set the base to 3 because it's tripling. If it was doubling, we could do it to 2. Or if it was quadrupling, let's say, we could do it to 4. But our base is going to be 3 in this case because we're tripling, right? So B, our bacteria population, equals 3. And then we don't actually know how much time it's going to take. So that's what we're actually trying to find, right? T is going to be our time. And if we come back up here, it says the bacteria triples every minute. So we know our time is in minutes, okay? So pretty simple. We've seen this before, right? We have a base, we have an exponent, and we have an argument. So based on what we had just learned, let's just dive in and write it as a log, right? So you have a log, if we want to rewrite this log, the base is 3, right? Our argument is B, the bacteria population, and that's going to equal the time it takes, okay? So let's review this again real quick. Our base is 3, so that's A. Our argument is B, that's our X. And we're all finding all of that is going to be what we're raising that to, T, right? That's our Y. That's our exponent, okay? So, but we're given our bacteria population. If we come up here, it already gives us that. That's what we're looking for, right? We're looking for the time it takes to get to that. So let's rewrite this, okay? Log base 3 to get to 2 times 10 to the 18 equals T, right? So we have log base 3, argument 2 times 10 to the 18, that's our population, should equal our T. But remember, this is in minutes, okay? And trickily, I just made that word up. It's not actually in the dictionary, but trickily, they included hours here. So we're going to have a little unit conversion. But you know what? If we want to do our little trick from earlier, let's get that page readily available. We're trying to find Y, right? And Y, to find Y, because it's the only one we don't know, right? That's our T. We're going to take the natural log of X and divide it by the natural log of A. So let's do that. So we're going to say that T equals the natural log of X, which is 2 times 10 to the 18, okay, over the natural log of our base 3. And that is all going to equal, let's do this on this calculator. And here's my little tip that I wrote up here because I knew we were going to get to this point. If you want to write times 10 to the 18th power in your calculator, there's a really easy way to do that without typing all of it out and getting super confusing. So you go natural log, okay, we get 2. And then we go second button, right? I wrote second up here, and then we're going to hit the comma button because that's the EE, the little blue EE right there above it. And we're going to go 18, okay? And that's what that's saying is 2 times 10 to the 18th, okay? So that's all fine and dandy. We're going to divide that by the natural log of 3. And this should give us our answer, right? So if we do that, it is going to take 38.36, rounding up, okay, minutes. Right? Because that's what we were doing originally. However, we want to know an hour. So we're going to have to do a little unit conversion. We are not done yet. Okay? So we're going to come down here, 38.36 minutes times, well, how many minutes are in an hour, right? We're going to put what we want to cancel on the bottom. So 60 minutes in 1 hour, right? Equals these cancel. So we're just going to do 38.36 divided by 60, okay? And that is going to give us 0.6, rounding again, 0.64 hours, roughly, okay? So what did we answer? We found out that bacteria tripling every minute on a Petri dish is going to take about half an hour, just over half an hour, right? 0.64 hours to get to a population of bacteria of 2 times 10 to the 18, okay? That is a lot of bacteria, mind you, but it would be surprising how fast this can actually happen in the real world. So with that, guys, hopefully that all made sense. If you haven't already, please like and subscribe. Share this channel with a friend if any of this was useful. Hopefully my cheat sheet here, the conceptual stuff, this really helps you guys out later on. But yeah, if you haven't already, subscribe. Thanks for tuning in, and you know what? I think next video I am going to do something on the unit circle. So if you are in pre-calc, you're still kind of hitting the jackpot, and I'm super stoked to get that one released. But anyways, guys, thanks for tuning in. We'll see you next time.